Thank you to the organizers for giving me the opportunity to be here today speaking to you. My name is Genevieve Pearson. I'm a graduate student at the University of Arizona working with David Sand. And today I'm going to talk to you about the ongoing search to find failed supernova in the nearby universe. So we know that red supergiants explode as type 2 core collapse supernovae. And we know that red supergiants can be up to at least 30 solar masses. However, when we look at the progenitors of type 2 supernovae, we find no progenitors with masses greater than 20 solar masses. So what is happening to these high mass red supergiants between 20 and 30 solar masses? These missing high mass red supergiants are referred to as the red supergiant problem. There are a few solutions to the red supergiant problem. It could be that this isn't a problem at all. We could just not have seen any of these high mass red supergiants explode yet. High mass red supergiants are rare, and the current mass function for supernova progenitors is within 3 sigma of the expected mass function if we include these 20 to 30 solar mass red supergiants. If it is actually a problem, there's a few other things that could be causing this. We could be getting our progenitor masses incorrect. One of the ways that we could be doing that is if there's a lot of dust in front of these higher mass objects, they would appear to be lower mass than they actually are. It could also be that these higher mass objects have a significant amount of mass loss at the end of their lives, causing them to explode as lower mass red supergiants once they've lost all that mass. And finally, the most exciting and flashy of the different solutions is that some of these high mass progenitors are imploding rather than exploding. So you're getting a failed supernova. This has long been predicted by theoretical models of these explosions. The black here is a failed supernova and the red is a successful supernova. And you can note that between 20 and 30 solar masses, many of these models are failing to create an explosion. So we're getting a lot of direct implosions. This is an exciting solution in that it also provides a pathway for us to be seeing these low mass black holes that we're seeing in LIGO detections and in black hole binaries. So of course, we've been looking for these failed supernovae. And so far there are 3 candidates in the nearby universe. The most exciting of which is NGC 6946BH1, which you can see here in the HST image on your right, was very bright supergiant in 2007, but by 2015 it had completely disappeared. And continued optical follow-up of this object shows it has yet to re-brighten in the optical. This is an LBT light curve, a large binocular telescope light curve of this object, and you can see it has not brightened in 15 years, which seems pretty convincing that this might be a black hole. I want to highlight here this initial transient event that happened before it disappeared. Some models predict that maybe these failed supernovae do have some kind of low luminosity transient that we'd be able to observe potentially as an alternative way of seeing these failed supernovae without actually seeing an individual star disappear. So how do you actually confirm that something is a failed supernova? Well, you have to look in the IR. If something is a black hole, you would expect there to be no IR light. So, of course, we propose to observe this with JWST, and we do, in fact, find a IR source. So here, the top circles, the ones in direct middle of each square, are the failed supernova candidate. And so you can see, particularly in these bottom squares here in the Miri filters, that it's incredibly bright, and in 21 microns, it's definitely a point source there. So we're seeing it in all the IR bands. What is this, if not a failed supernova? It's been disappeared in the optical for 15 years. Well, there's 2 different possibilities. Firstly, it could still be a failed supernova, and then the IR emission we're seeing is some result of accretion onto the black hole. However, the issue with that is it's been gone for 15 years, so that places some limits on how bright it can be in the IR, based off of how much material is possible to accrete onto this black hole. It could also be some kind of outburst that formed a dust shell around this star. But when we model this outburst, we find that it's fainter than the pre-disappearance star. So that would match up with an expectation of some kind of merger product where you have two bright sources spiraling in, slamming together, creating its outbursts, and then we have a dust shroud, and the remaining star is fainter than the combined previous two stars. Ultimately, to decide between these two different possibilities, we really need JWST spectra in order to distinguish between the two. And we can't say for sure that this is indeed a failed supernova. And this is our best candidate thus far. So my involvement with searching for failed supernova is mostly focused on the HST failed supernova project, which is looking at 31 nearby galaxies which have high core collapse supernova rates, and also more than 2 epochs of F814 archival HST imaging. As part of our Cycle 26 program, we imaged all of these galaxies in F814 so that we could get a reference image, so we can leverage the entire 30+ year baseline of HST to see if we see any of these stars disappear. Based on current predictions of failed supernovae, that should result in between 5 and 20 failed supernova candidates. So how do we do this? Firstly, we take our raw data. We have our reference image, which was taken as part of our Cycle 26 program, and our archival data. So that's any data that is not in the epoch of the reference image. That isn't an F814, so it could be before or after. And then we align those two images together, and then we subtract them using Zogi. We take that difference image and we identify sources using source extractor on it. Then, in order to determine which of these identified sources are actually real good candidates, we choose a selection criteria such that when we place fake stars in our archival image and run that fake star image all the way through our process, our selection criteria will find the majority of our fake stars. So when we use that selection criteria on our real data, we can have a good candidate population. We then take those candidates and we vet them by looking at other HST filters. Many of these observations have alternative archival data outside of F814, by doing ground-based observing with MMT and the Large Binocular Telescope. And in the cases where some of these have JWST imaging in the archive, we also look to see if that source is still in JWST. So then this creates a gold sample of failed supernova candidates that we can report. So, of course, what have we found? So far, we're about 50% of the way through analyzing the HST archival data. And we have found one candidate, M51DS1, which is a yellow or red supergiant. It's a massive star that right in the regime we'd expect it to be, that underwent an exceptional dimming event in 2019. You can see it's visible in 2005 and in 2016, but gone in 2019. And that's a drop of more than 2 magnitudes. So we are very, very excited about this. We found a failed supernova, except when we re-imaged it in 2021, it had reappeared. So no longer is this a disappearing star, but rather a reappearing star. We think this might have been the result of some kind of mass loss event, like a more extreme version of the Great Dimming of Betelgeuse. So it was shrouded by mass, and then as time went on, we finally were able to see the star again. So punchline here, we haven't found any failed supernova as part of this search. And we're already 50% of the way through the sample. It's possible we could find 5 or so failed supernova candidates in the remaining 50%, but it's very unlikely we'll find 20. So we're already pushing to that lower end of the expected sample. So what does this look like in the era of LSST? How do we find failed supernova then? Well, our HST search will place a stringent upper limit on the failed supernova rate. And from there, we can figure out how many we expect to find in LSST, if we expect to find any at all. LSST will be great at detecting any faint outburst events. So if we have a faint transient associated with a failed supernova, we should be able to find them. Of course, this has issues in that merger events and other types of transients might also populate the sample, so it's going to be difficult to disentangle them. And in nearby galaxies, so distances less than 15 megaparsecs, where you can see individual stars disappear, there we can actually observe these stars, seeing if disappearing sources. of course, we're going to have a lot more of these imposter objects that we're seeing with the depth of LSST, but the cadence of LSST will let us see those rebrighten. So these imposter objects are going to be really exciting in their own right for continued study, but we really need to leverage the more red bands of LSST, so I, Z, and Y, so that we can see through any dust that is surrounding any of these massive stars that would hide as failed supernovae. So ultimately, any failed supernova candidates we see will need IR follow-up, particularly with J2ST, but also with Roman as well. We're very excited about Roman with failed supernova searches. And in summary, failed supernova are this really exciting solution to the failed supernova problem, but we haven't actually confirmed that any of them exist. So our HST archival data will provide a strong upper limit on the failed supernova rate, but so far, all we can confidently say is that these failed supernova searchers are finding a lot of these extreme variable objects, which we haven't been able to see before, that are a known unknown that we'll find a lot of with LSST. Thank you, and I'll take any questions.